Okay, let's look at our last example here. Again, I did skip an example on the book with graphing an exponential, it was an exponential function with e to the x in it. The reason that I skipped that is I'm not going to test you on that. Truly, the two that I would test you on, there's going to be one that's going to be a polynomial function, like the first two examples. There's going to be one that's a rational function, like examples 3 and 4 in this one. So those are the only two types of questions that I'm going to test you on. So that's what I wanted to emphasize. But I did want to cover this last example that they do in the textbook. And this is the example 4 in the textbook. It's example 5 for us. This is graph and analyze f of x equals 2x to the 5/3 minus 5x to the 4/3. And you'll notice quickly here that I have things written down a little wrong. So for instance, it says vertical asymptotes and horizontal asymptotes. In this case, we don't have any of those, but that's okay. We can simply write none in those blanks. So what's the domain of these functions? Well, the domain of these functions, if you notice, these are both cube roots. And because they're cube roots, if it's square roots, we'd have a restricted domain. But because it's cube roots, which is an odd root, we know that our domain here is going to be negative infinity to infinity. There's no restrictions on odd roots. We want to find those x-intercepts, and again, to find the x-intercepts in this case, you set the function equal to 0. So let's try that. If we set 2x to the 5/3 minus 5x to the 4/3 equal to 0, what could we do? Well, we could factor this, and in fact what we could factor out is an x to the 4/3. When we do that, what we would be left with, well, 2x to the 5/3 divided by x to the 4/3 would be 2x to the 1/3, and then minus 5x to the 4/3, take away the x to the 4/3, you would just have minus 5. And so that would equal 0. So then we'd have x to the 4/3 equals 0. Well, that would be cubing both sides, you'd get 0, and then taking the 4th root of both sides, you would also get 0. So that gives me x equals 0, period. Now I have 2x to the 1/3 minus 5 equals 0. Add 5 to both sides, I'd have 2x to the 1/3 equals 5. Divide both sides by 2, I'd have x to the 1/3 equals 5/2. And then to get rid of that cube root, you actually cube both sides. So what I do is I cube 5 and 2 individually, so I'd have x equals, well, 5 cubed is 125, and 2 cubed is 8. So what does that tell me? That tells me that I have two x-intercepts of 0, 0, and 125 eighths. 0. And I'm no doubt about it, when I graph that, what I'm going to do is use a calculator in the decimal version of that to see what it is. So x-intercepts again were the points 0, 0 and 125 eighths 0. Y-intercept, I already know what it is if you have some insight. I already know that the point 0, 0 is an x-intercept, and the second 0, 0 is an x-intercept. It's also a y-intercept. But how do I get an x-intercept if you wanted to do it individually? You just plug in 0. So 0 to the 5/3 is 0, times 2 is 0. And 0 to the 4/3 is 0, times 5 is 0. So that gives me 0. So again, there's the mathematical version of showing that it's 0, 0. But again, I already knew that. Vertical asymptotes, there's no place where this isn't a rational function, right? So this isn't a fraction. So there's no place where it equals, the denominator equals 0, so that's none. Horizontal asymptotes, you're looking at the limit as x goes to infinity and the limit as x goes to negative infinity. Well, in this case, when you look at the limit as x goes to infinity and negative infinity, you have infinite values here. So it's either going to be going to infinity or negative infinity. There is no horizontal asymptote, so there is none. So really, I messed up by putting vertical asymptote and horizontal asymptote there on this problem. Those shouldn't have even been included because it's not a rational function. Okay, so let's go ahead and look at this. When is this function increasing or decreasing? Well, we need to look at the derivative of this function. Again, what was our original function? Well, it was 2x to the 5/3. So the derivative of 2x to the 5/3 would be 2 times 5/3, or 10/3, x to the 5/3 minus 1, which would be 2/3, minus 5 times the derivative of 5x to the 4 thirds, which would be 5 times 4 thirds, which is 20 thirds, x to the 4 thirds minus 1, which would be 1 third. So my derivative that I'm getting is 10 thirds x to the 2 thirds minus 20 thirds x to the 1 third. That's going to be the version that I use to find the second derivative, but in order to find the critical values, I want to factor this. So if I factor this, I notice that I can pull a 10 thirds out in both. And if I pull it in, I can also pull out an x to the 1 third. So if I pull out a 10 thirds x to the 1 third, in the first term, dividing it by 10 thirds, my coefficient's 1, x to the 2 thirds divided by x to the 1 third would leave an x to the 1 third, minus 20 thirds divided by 10 thirds would be a 2, and then the x to the 1 third divided by x to the 1 third just goes away. That simplifies to a 1, right? So the factored version of the derivative is 10 thirds x to the 1 third times x to the 1 third minus 2. So why do I care about that? I need to set the derivative equal to 0. This is never undefined, so we don't need to worry about that. So 10 thirds x to the 1 third would equal 0. Multiply both sides by 3/10, so I'd have x to the 1 third equals 0. Cube both sides and I'd get x equals 0. So at x equals 0, I have a critical value. And then I also have to look at x to the 1 third minus 2 equals 0. Add 2 to both sides, I'd have x to the 1 third equals 2. Cube both sides, and I'd have x equals 8. So these right here, 0 and 8, are my critical values. Again, why do I care about critical values? Because I need to break up my number line on those critical values, 0 and 8. Those could be potential maxes and mins. So my derivative at those points are 0. I know my first interval is negative infinity to 0. Second interval is 0 to 8. Bad looking 8 there. And then my third interval is an 8 to infinity. What do I want to do? I want to test points in each one of those intervals. Again, I'm plugging it into the derivative, and I'm going to plug it into the factored form of the derivative, I guess. Really doesn't matter too much on this one, in all honesty. 10 thirds x to the 1 third, all times x to the 1 third minus 2. Okay, something less than 0. How about negative? Ooh, I need a cube root of it, right? So how about negative 27? That's a nice number. That's got a cube root, right? A number between 0 and 8. Well, a nice number to take a cube root of would be a 1. And a number bigger than 8. Well, I'm going to be taking a cube root of it again, so I'll choose the number 27 because the cube root of that number is nice. Okay, so let's try negative 27. Negative 27, the cube root of that's negative 3. So that first term would be a negative. And cube root of 27 again is negative 3 minus 2. That would also be negative. And a negative times a negative is a positive. So that first entire interval must be, the derivative must be positive. Plug in a 1. Cube root of 1 times 10 third is a positive. Cube root of 1 third is 1 minus 2 is a negative. A positive times a negative is a negative, so the derivative has to be negative on that entire interval. Go to our third interval, the number 27. Cube root of 27 is positive times 10 thirds is positive. Cube root of 27 is 3 minus 2 is positive, and a positive times a positive is positive. Anywhere my derivative is positive, my function is increasing. So that's on negative infinity to 0 and 8 to infinity. Anywhere my derivative is negative, that's decreasing, so that's 0 to 8. First derivative test says it is defined there. It changes from increasing to decreasing at x equals 0. That's a maximum. First derivative test says it is defined there, and it changes from decreasing to increasing at that point when x equals 8. That must be a minimum. And again, that's just saying that when that's the x value, I need to actually find the y value. So how do I find the y value? Well, I have to plug it back into the original function. So let me zoom out a little bit so I can see the original function. That was 2x to the 5 thirds minus 5x to the 4 thirds. The numbers that I needed to plug in there are the numbers 0, which thank goodness we've already plugged that in and we got 0. So that tells me the point 0, 0 is a maximum. And then I need to plug in the number 8. So if I plug in 8, please plug that into your calculator now. 8, whatever the y value is, I know that's going to be a minimum. So I'm going to plug this into my calculator real quick. When I plugged in 8, I got a value of negative 16. So 8 negative 16 has to be a minimum. So let me put down that maximum and minimum while I'm looking here. The maximum is at the 0.00, and that minimum is at the 0.8 negative 16. My increasing intervals are wherever that derivative was positive, which was the intervals negative infinity to 0, and also the interval 8 to infinity. My intervals of decreasing was anywhere where my derivative was negative, and that was on the interval from 0 to 8. So that's all the information I need from the first derivative. Now let's move on to analyzing the second derivative to determine concavity.